Welcome to our Quantum Deep Dive.
Great to be here.
Today we're diving into, well, a really fascinating area. It's where the absolute cutting edge of computing meets a pretty fundamental need in data analysis. I'm talking about feature selection.
That's right.
We're basing our discussion today on the essay Quantenunterstützte Feature-Auswahl, Optimierung neu gedacht by Jörg O. Schneppert.
A really insightful piece.
It really is. Now, feature selection. Think of it like carefully picking out the most powerful ingredients for a recipe. You want to get rid of anything that doesn't really add value.
Exactly. So the final dish or data model in this case is as, insightful and effective as it can possibly be.
So our mission today in this deep dive is really to get a handle on how this seemingly abstract world of quantum computing could actually revolutionize the selection process, especially for really complex data sets. We want to offer you a bit of a shortcut, really, to understanding this advanced topic and, well, its potential impact.
Yeah, and as Schneppert outlines in his essay, feature selection is fundamentally about finding that most informative subset of features from a much larger pool.
So like the signal from the noise?
Precisely. Mathematically, you could frame it as picking the best subset S from a bigger set X to optimize some task, which we usually represent with a cost function, JS.
Okay.
And it's not just about using fewer features, although that's part of it. It's about boosting model accuracy by throwing out the noise, speeding up calculations.
Which is always good.
Always good. And making the results easier for us humans to actually understand.
And you mentioned it's different from feature engineering.
Right. Feature engineering is more about creating new features, maybe combining existing ones. Selection is about choosing from what's already there.
Got it. Okay, so why is this selection process, picking these powerful ingredients, as I called them, why is that such a challenge with the massive data sets we have today? What makes it so tough?
Yeah. Schneppert's essay really nails the key problems here, especially with large, intricate data. The big one. It's called combinatorial explosion.
Sounds dramatic.
It kind of is. If you have, say, n features, the number of possible subsets you could choose is 2 to the power of n. That number gets astronomically huge, incredibly fast.
So trying every combination is just out of the question for classical computers.
Absolutely impossible for large n. Then there's the sheer computational effort needed to evaluate these subsets, especially for what are called wrapper methods.
We'll get to those, I assume.
We will. But basically, they involve building and testing a model for potentially many, many subsets. That takes a huge amount of time and processing power.
Right, and it's not just the sheer number of features, is it? Sometimes features can be, well, related, telling similar stories.
Exactly. That's the issue of correlation or multicollinearity. When features are highly related, it's really tricky to figure out which one or which combination is truly driving the insights. It muddies the waters.
And that confusion could lead the model astray.
It can. And finally, there's the ever-present risk of overfitting. If you throw too many features in, especially noisy or irrelevant ones, your model might learn the training data too well.
So it looks great on the data you trained it on.
But then it fails miserably when it sees new, unseen data. It hasn't learned the general patterns, just the quirks of the training set.
Okay, so that really sets the stage for why we need new approaches, which brings us squarely to the core of Schneppert's essay, how quantum computing might offer a path forward. Now, for those of us, including me, who aren't quantum physicists, can you break down the absolute basics? Why could quantum computers potentially be so much better at this kind of optimization problem?
Sure. So quantum computing basically leverages the, let's say, weird but powerful rules of quantum mechanics to do calculations. The essay highlights 3 key principles: superposition, entanglement, and quantum parallelism.
Okay.
Think of superposition first. A normal computer bit is either a 0 or a 1. Simple. A quantum bit or qubit can be a 0, a 1, or crucially, a combination of both at the same time.
Both at once. How does that work?
It's one of the core quantum phenomena. Mathematically, we write its state as alpha rangle plus beta 1 rangle, where alpha and beta tell you the probability of measuring 0 or 1. Then there's entanglement.
The spooky action at a distance.
That's the one Einstein famously called it. It's this incredible connection where 2 or more qubits become linked. Their fates are intertwined, no matter how far apart they are. Measuring one instantly affects the other.
Wow. And the third one, parallelism.
Quantum parallelism flows directly from superposition. Because a qubit can be in multiple states at once, a quantum computer can essentially perform many calculations on all these possibilities simultaneously.
Ah, okay. So instead of checking feature combinations one by one, like a classical computer,
A quantum computer could, in a sense, explore a vast number of them in parallel.
that sounds like where the real speed up comes from.
Exactly. This inherent parallelism, the ability to navigate these enormous possibility spaces efficiently, that's why quantum computing is so exciting for these complex optimization problems where classical methods just get stuck.
And Schneepat points to specific quantum techniques.
Yes, the essay mentions a few relevant ones. Quantum annealing, which kind of uses quantum effects to settle into the best solution.
Like finding the bottom of a valley.
That's a good analogy.
Right.
Then there's Grover's algorithm, famous for speeding up search problems, and also hybrid approaches like QAOA, the quantum approximate optimization algorithm.
Okay, so the central argument in Jurgo Schneepat's work here is that these quantum capabilities could be harnessed to really tackle feature selection, especially for those massive high-dimensional data sets.
That's precisely it. The essay digs into how these quantum-assisted methods could potentially blow past the limitations we hit with traditional techniques.
Now, before we go deeper down the quantum rabbit hole, Schneepat's essay also grounds us in how we currently do feature selection. Classically, can we quickly run through the main approaches?
Absolutely, it's good context. Classical methods generally fall into three main buckets: filter, wrapper, and embedded methods.
Filters first.
Filter methods are usually the first pass. They evaluate features individually, often using statistical schools like correlation coefficients or chi-squared tests. They're fast, computationally cheap.
But the downside?
They look at each feature in isolation.
Yeah.
They don't really consider how features might interact with each other, which can be really important.
Right. So wrapper methods.
Wrappers are more sophisticated. They actually use the machine learning model you intend to train as part of the selection process. They try different subsets of features, train the model, test its performance.
Ah, so they see how the features work together in the context of the actual model.
Exactly. Methods like recursive feature elimination, RFE, or forward backward selection fall here. They can be very powerful and find really good feature sets.
But I sense a but coming.
The but is computation time. Because you're potentially training and evaluating lots and lots of models, wrapper methods can be incredibly slow and resource intensive, especially with many features.
Okay, and the third type, embedded.
Embedded methods cleverly integrate the feature selection right into the model training process itself. Think of algorithms like lasso regression, which adds a penalty that shrinks the coefficients of less important features towards zero, effectively selecting them out. Or decision trees, which naturally select features at each split.
So they kind of do the selection on the fly as they learn. A good balance, maybe?
Often, yes. They tend to offer a good trade-off between the performance you might get from wrappers and the efficiency of filters.
So we have these classical tools, but as we established, they hit walls with really big, complex data. Can we dig a bit deeper into what the essay identifies as their main limitations there?
Sure. The absolute killer, as Schneepat points out, is scalability. That combinatorial explosion we mentioned, too, to the power of n possible subsets. As n the number of features grows, the search space becomes unmanageably vast.
Makes sense.
This isn't just theoretical. It translates directly into huge increases in computation time memory needs, making exhaustive searches completely impractical. You have to resort to heuristics or approximations that might not find the truly optimal set.
And what about the data itself, if it's messy?
That's the other major challenge the essay highlights. Dealing with noisy or incomplete data, irrelevant information, missing values.
Right.
These can seriously confuse classical methods trying to assess feature importance. It's hard to tell what's truly predictive when there's so much clutter.
Okay, that really clarifies the classical struggles. Let's pivot back to the quantum side. We touched on qubits. Can you maybe elaborate a bit more on what makes them so fundamentally different from classical bits? Why is that difference the key?
Right, so a classical bit fundamentally is a switch. On or off, 1 or 0. A qubit, thanks to superposition, is more like, well, a dimmer switch. It can be fully on, fully off 0, or crucially exist in a state that's a combination of both.
A psi wrangle, alpha wrangle plus beta 1 wrangle thing.
Exactly. Alpha squared and beta squared represent the probabilities of getting 0 or 1 if you measure it. But until you measure, it holds both possibilities. This both at once capability is the bedrock of quantum parallelism.
And entanglement adds another layer.
It does. It links qubits. Imagine that 3-1 Swartor wrangle plus 11 wrangle state for 2 entangled qubits. If you measure the first qubit and get 0, you instantly know the second one is also 0. If you get 1, the second is 1. They're perfectly correlated. This allows for complex correlations and information transfer within the computation.
But eventually you have to get a classical answer out, right?
You do. That's the measurement step. When you measure a qubit, or an entangled system, the superposition collapses. It snaps to a definite classical state 0 or 1 according to those probabilities alpha 2 and beta 2.
So the quantum magic happens during the computation before the measurement.
Precisely. The power lies in exploring that vast space of possibilities using superposition and entanglement during the calculation.
It's definitely counterintuitive, but I can start to see how exploring many paths at once could be revolutionary for optimization, like finding the best feature set. Now, Schneppat's essay mentions some specific quantum algorithms, Grover's, quantum annealing. Can you give us a bit more flavor on those?
Sure. Grover's algorithm is designed for unstructured search. Think finding a name in a phone book without any order. Classically, on average, you'd check half the entries, right? So n2 steps for n entries.
Roughly.
Grover's can do it in roughly the square root of n steps. That's a quadratic speedup, which is significant for large n. The essay mentions it works using something called amplitude amplification, basically boosting the probability of measuring the state corresponding to the correct answer.
Okay, faster searching. What about quantum annealing?
Quantum annealing is specifically geared towards optimization problems. The idea is to encode the problem like finding the best feature subset into the energy landscape of a quantum system, described by something called a Hamiltonian.
The HT, 1THB plus THP equation?
Exactly. You start with a simple known low energy state, HB, and slowly, adiabatically, evolve the system towards the Hamiltonian that represents your complex problem, HP. Quantum effects like tunneling help the system explore the landscape and, ideally, settle into the global minimum energy state, which corresponds to the optimal solution.
So it finds the best answer by finding the lowest energy configuration.
That's the core principle.
And the other two mentioned, VQE and QAOA, they sounded like hybrid approaches.
They are. Both VQE, variational quantum eigensolver, and QAOA, quantum approximate optimization algorithm, bridge quantum and classical computing. VQE is often used for chemistry problems, but also optimization. It uses a quantum computer to prepare a trial state based on some parameters, measures its energy, and then uses a classical computer to adjust those parameters to find the state with the lowest energy. It's an iterative process.
So the quantum computer does the hard bit of calculating the energy for a given configuration.
And the classical computer does the optimization loop, figuring out how to change the configuration. QAOA is similar, but tailored more for combinatorial optimization, like our feature selection problem, or things like the max cut problem. It also uses a parameterized quantum circuit and classical optimization.
These hybrid methods sound quite practical, especially given the current state of quantum hardware, which Schneppat's essay touches on too, right? Who are the main players?
Yeah, the essay gives a snapshot. Companies like IBM have been steadily increasing their qubit counts, now over 100. Google made waves with their Sycamore processor, claiming quantum supremacy, performing a task essentially impossible for classical supercomputers. Rigetti is another key player, offering cloud access to their quantum processors.
But there's always a but with emerging tech. The essay mentions limitations.
Absolutely. We're firmly in the NISQ era, noisy intermediate scale quantum. Intermediate scale means qubit counts are still relatively modest, maybe dozens to a few hundred. Noisy is the big one.
Meaning errors.
Meaning errors, yes. Qubits are incredibly sensitive to their environment. Noise causes decoherence where they lose their quantum properties. This leads to errors in computation. We don't have robust quantum error correction yet for these machines.
So they're powerful in principle, but fragile and error-prone in practice right now.
That's a good summary. It limits the depth and complexity of algorithms we can reliably run.
Okay, so putting it all together, the potential of quantum parallelism, the specific algorithms like annealing and QAOA, but also the NISQ limitations.
Yeah.
How does Schneppat's essay suggest we actually use quantum computing for feature selection, realistically?
The core strategy, as the essay lays out, is leveraging that parallel search capability. Remember the two-Theron problem. Quantum computers, even NISQ ones for smaller n, can potentially explore that exponential search space much more effectively than classical brute force or even heuristic methods.
So using quantum annealing or QAOA to directly hunt for that optimal feature subset.
That's the potential payoff. These methods are designed to find global optima, which could lead to significantly better feature sets, especially in high-dimensional complex spaces where classical methods might get stuck in suboptimal solutions.
How do you actually tell a quantum computer what the feature selection problem is? You mentioned QUBO earlier.
Right, you need to translate the problem.
Hmm.
Feature selection is fundamentally an optimization task. You want to minimize prediction error while maybe also penalizing the number of features used, like JS, error S plus lambda times S.
Minimize error, but keep it simple.
Exactly. This kind of task can often be reformulated into that standard mathematical form called quadratic unconstrained binary optimization, or QUBO. It uses binary variables, 0 or 1, representing feature included or not, and expresses the objective as a quadratic function.
And QUBO is like a language quantum annealers understand.
It's a common input format, yes. For annealing, the QUBO formulation is mapped onto that Hamiltonian we discussed, A equals sum AI plus sum BASJ. The annealer then physically tries to find the lowest energy state of that Hamiltonian, which directly tells you the optimal assignment of the binary variables, i.e. the best feature subset according to your cost function.
Fascinating. And what about those hybrid approaches in this context? How do they fit in for feature selection specifically?
They're seen as really promising for the NSQ era. The essay suggests a workflow. Maybe start with classical preprocessing. Use fast filter methods to weed out obviously useless features, reducing the problem size.
Make the quantum part easier.
Exactly. Then feed that reduced but still complex problem to a quantum optimizer, maybe QAOA or an annealer, to find the best subset among the remaining candidates. And finally, use classical machine learning to validate the chosen features, maybe fine-tune the final model.
Best of both worlds, potentially. Using classical speed for the easy stuff and quantum power for the hard optimization.
That's the idea. Leverage each technology for what it does best right now.
Okay, this is starting to feel more concrete. Schneppat's essay also gives examples of where this could actually make a difference. What fields might benefit?
Several high-impact areas are mentioned. Bioinformatics is a prime example. Imagine trying to find which few genes out of thousands are linked to a specific cancer. That's a massive feature selection problem.
Perfect fit for this, it sounds like.
Potentially, yes. The essay suggests quantum annealing could sift through those gene combinations much more effectively than classical methods. Finance is another area identifying the key market indicators or economic factors driving financial risk from huge datasets.
High stakes there.
Definitely. And healthcare generally. Think about developing diagnostic algorithms using patient data imaging, genomics, clinical notes. Selecting the most predictive features is critical for accuracy in diagnosing diseases like diabetes or heart conditions. Quantum-assisted selection could lead to better, faster diagnoses.
These examples really drive home the potential impact. But Schneppat is also realistic about the hurdles. What are the big challenges and limitations holding this back right now?
The essay lays them out clearly. First, the technological hurdles with NISQ computers we discussed. Limited scale, qubit count, high error rates, qubit instability decoherence. These restrict the size and complexity of problems we can actually solve reliably today.
The hardware just isn't quite there yet for the really big problems.
Not for truly massive, complex feature selection tasks, no. Then there are theoretical and practical boundaries. It's not always straightforward to optimally translate a specific feature selection problem into the right format, like QUBO for a quantum algorithm. That translation itself is a research challenge.
So even if the hardware was perfect, figuring out how to ask the question correctly is hard.
It can be. Plus, we lack standardized benchmarks.
Yeah.
It's hard to definitively compare a quantum approach against a classical one and say, yes, the quantum way was truly better for this real-world problem, because fair comparison is tricky.
And I imagine cost and expertise are factors too.
Big ones. Accessing quantum hardware is expensive, whether building or using cloud services. And you need people with deep expertise in both quantum physics and machine learning, which is still a rare combination.
So quite a few significant challenges remain. Despite that, what's the outlook? What future perspectives does Schneppat highlight? Where is this field heading?
There's definitely optimism grounded in expected progress. On the hardware front, the expectation is continued growth in the number of stable, high-quality qubits. Lots of work on better materials, cryogenics, different qubit types like trapped ions.
Aiming for lower noise, better stability.
Exactly. And alongside hardware, algorithm development is key. Creating algorithms that are more robust to noise or specifically designed for NISQ capabilities like improving VQE and QAOA, and of course, the long-term goal of fault-tolerant quantum computing through error correction.
How about integrating these tools into how data scientists actually work?
That's crucial. The essay sees hybrid systems becoming more common, embedding quantum optimization steps within larger classical data science pipelines. Cloud platforms making quantum resources more accessible will play a big role here.
So not necessarily replacing classical methods entirely, but augmenting them.
For the foreseeable future, yes. Combining strengths seems the most likely path. Quantum for the specific optimization bottlenecks, classical for everything else.
And looking even broader, what about the societal or economic implications?
Well, if this pans out, the impact on data-intensive industries like bioinformatics, finance, and healthcare could be transformative. Faster drug discovery, more accurate financial modeling, better medical diagnostics, leading to new innovations. But the essay also rightly raises ethical flags.
Such as?
Data privacy and security in the quantum era is a big one. Quantum computers pose a threat to current encryption. Ensuring responsible use of this powerful analysis capability, avoiding bias, and addressing potential inequalities in access to quantum resources are all critical considerations.
Okay, this has been a really comprehensive deep dive, mapping out both the exciting potential and the present hurdles of quantum-assisted feature selection. It's clear Yorgos Schneppet's essay provides a great framework for thinking about this. If we were to boil it down, what are the absolute key takeaways for you?
I think the main message is that quantum computing genuinely offers promising new avenues for feature selection. Its ability to handle complexity through parallelism and specialized algorithms like annealing and QAOA could really help us overcome classical limitations, especially with these enormous data sets we're generating.
But with a healthy dose of realism.
Absolutely. The challenges are significant, the hardware isn't mature, formulating problems is tricky, benchmarking is hard, and it requires specialized skills and resources. It's still early days.
So as we wrap up, it leaves us with a compelling picture. Quantum computing holds this immense potential to reshape data analysis, maybe even decision-making, across many fields. It certainly gives you, the listener, a lot to think about the transformative power, but also the responsibilities that come with such potent technology.
Well said.
And once again, our exploration today was guided by the insights in the essay Quantenunterstützte Feature-Auswahl, Optimierung neu bedacht, by Yorgos Schneppet. A fascinating read if you want to delve even deeper.